Hey guys, welcome back to another lecture video for Chem 115. This is part 2 of buffer preparation calculations. In the previous lecture video, we finished solving for the number of grams that's required to prepare a buffer solution that originally had ammonia in it. And so we're going to look at another example, example number 2. We're going to see how we can use the Henderson-Hasselbalch equation in different ways to determine the mass or the volume that's required to prepare our buffer solution. And so reading through example number 2, it's asking what volume of 0.100 molar acetic acid and 0.100 molar of sodium acetate is required. So what volume is required of these two substances at a specific concentration to produce 1,000 milliliters of buffer at a pH of 4.000. So the pKa of the weak acid is 4.752. So we're going to go ahead and use this information and determine how much volume of the buffer are we going to measure out to create a 1,000 milliliter buffer solution at a pH of 4.000. And so before we dive into the calculations, once again, I want to take a step back and illustrate what this problem is really asking us to do. And so reading through the problem on your own, there's a couple of things that I do want to mention. So these two concentrations, they are representing the stock concentration. So for example, if you had two stock solutions such that one stock solution represented the 0.100 molar of that acetic acid, and the other stock solution is representing the 0.100 molar stock solution of sodium acetate, how much of acetic acid and how much of sodium acetate, how much volume more specifically of acetic acid and sodium acetate will we need to create 1,000 milliliters of this acetic acid acetate buffer system. Okay. And so here what we're really trying to address is how much volume do we need from both of these stock solutions to create our buffer. Okay. All right, and so because they gave me a pH of 4.00 and the pKa is 4.752, and since I'm working with a buffer system, all of these clues kind of lead me to think about the Henderson-Hasselbalch equation. And so we're going to see what part of the Henderson-Hasselbalch equation we can use to determine how much volume of substance that we need to make this 1,000 milliliter buffer. Okay. And so the the Henderson-Hasselbalch equation is equal to the pKa plus the log of typically the conjugate base over the weak acid. Okay. And so I'm going to go ahead and identify the specific substance that we're going to be plugging into this Henderson-Hasselbalch equation. And so sodium acetate, that's going to be NaC2H3O2. And so if you guys recall, sodium is typically our spectator ion, and it doesn't affect the pH of our solution. And so we can go ahead and just focus on the acetate portion, and that's going to give me my base. Whether you guys perceive it as the conjugate base or the weak base, they're both interchangeable depending on the perspective of how you guys are looking at the reaction. Now acetic acid, it's going to be HC2H3O2. Okay. And so this whole item is going to represent our acid. Now, because acetic acid and acetate, there's a lot of like elements and numbers to write, I'm going to go ahead and create some abbreviations. And so I'm going to abbreviate the acetate portion as simply AC, right? So AC is representative of the acetate portion. And I'm going to go ahead and bring up the hydrogen. And so if I add both of them together, the symbol that I'm going to be using for acetic acid is HAC. Okay. So acetic acid is going to be this guy. And so since I'm abbreviating acetate as AC, then it would make sense for me to just represent this whole chemical formula as AC with a negative charge, to represent the negative charge on the acetate. Okay. All right, so this is going to be acetate, and this is acetic acid. And so I'm going to go ahead and use these abbreviations for my Henderson-Hasselbalch equation. And so since the Henderson-Hasselbalch equation has the conjugate base at the very top, the numerator, I'm going to go ahead and represent that as AC minus. And the denominator is going to be HAC, or acetic acid. Now, once again, this bracket is representing molarity. And if you guys recall, molarity is a ratio of moles per volume. And so if you guys are looking at what the question is asking us to find, we're trying to determine the volume of each of these substances that we're going to put in another beaker to make our buffer. And so since we have two concentration units right on top of each other, we can go ahead and cancel some stuff out. So we can go ahead and cancel out moles and moles. And what we're left is something per liter, right? So it's 1 per liter. And so the pH is equal to pKa plus the log of the volume of acetate in a per liter unit. And this is going to be the volume of acetic acid in a per liter unit. Okay. And so that's pretty cool because now everything in the Henderson-Hasselbalch equation in the parentheses is representative of volume units. And we're going to go ahead and use this ratio to help us determine how much volume is required of each substance to create our buffered solution. All right, and so we need a couple things. We need to figure out the pH and the pKa. So the pH is already given to us to be 4.000, and the pKa, I believe it was given to us. We didn't really have to convert it. It's 4.752. Okay. So 4.752 is the pKa. All right. And so if you guys look at the amounts, we have 0.100 molar and the same concentration for both acetic acid and sodium acetate. Since they're in concentration units, we're not going to actually plug them in to my Henderson-Hasselbalch equation just yet. The reason why is because how I've set up my Henderson-Hasselbalch equation is expressing specifically volume or per volume. And so I'm going to go ahead and leave the parentheses as is. So I just have the volume of acetic acid, or I'm sorry, the volume of acetate on a per liter basis divide this by the volume of acetic acid in a per liter basis. And so this ratio that is left over is what we're going to solve for in this Henderson-Hasselbalch equation. So I'm going to go ahead and subtract 4.752. And the value that I get here is going to be negative 0.752. That's going to give me my log of, this is going to be too much to write over and over again, so I'm just going to cheat just a little bit and duplicate it. Maybe I'll copy it. Who knows when I'll need it again. And so I'm going to go ahead and solve this ratio by taking the base 10 of both sides. And so this value gives me 0.177. And that's going to equal to this ratio. All right, so notice that I have this value 0.177 that's equal to the volume of acetate on a per liter basis and the volume of acetic acid on a per liter basis. So we don't want anything in terms of per liter. We want things in terms of liters. And so what that's going to do, what we're going to do is we're going to have to take the reciprocal of both values. So in other words, we're going to flip. So we're going to flip this guy. So let's just say that this is over 1. So when we take the reciprocal on the left-hand side of the equal sign, I get 1 over 0.177 is equal to the volume of acetic acid, but instead of a per liter basis, since we took the reciprocal, it's going to be on a liter basis. So now that we have it in the correct unit. And the reason why I didn't flip it at the very top over here is because it's still being logged, if you will. And so I don't want to mess anything with logs. I want to get rid of that log before I can flip anything inside it. And so here I have volume of the acetate in, once again, a liter basis. And so if you plug this into your calculator, what you get is 5.649717 continues. And so since there's like 3 sig figs here, I'm just going to go ahead and make sure I'm keeping 3 sig figs. And so that's going to give me this volume right here. And so what I'm going to do is I'm going to solve for, I'm just going to move some terms around. I'm going to move this guy over. So I have 5.65 times this by the volume of my acetate. And that's going to equal to the volume of my acetic acid in liters. Okay, so this is going to be in liters. And so if you look at what we got from the Henderson-Hasselbalch equation, what we got was an expression. We got a ratio that tells us the relative ratio between acetate and acetic acid. But this doesn't really solve the problem because we have 2 variables. So we still don't know this guy and we still don't know this guy. And so we're kind of at a standstill. And so whenever you guys are at a standstill, let's go ahead and go back and think about the concept. So if you recall, we're going to take some amount of each component, some amount of acetic acid, some amount of sodium acetate, put them in this beaker, and the total volume is 1,000 mils. And so we can actually write another expression to describe the relative volume or the needed volume of acetic acid and acetate, such that the volume of acetate, I apologize, in liter units plus the volume of acetic acid in liter units is equal to, so the total volume, well, I'll just go ahead and write it here. And I'll just continue. So total volume is 1,000 milliliters. And so notice that my unknowns, my variables, are in units of liters, and so what that is going to prompt me to do is just temporarily convert milliliters into liters. And so for every 1.00 liter, that's equal to 1,000 milliliters. So I'll just go ahead and put that over here. So 1,000 milliliters is equal to 1 liter. And so we're simply going to take this milli, which is times 10 to the negative 3, and move this decimal 3 places to the left, okay, giving us 1 liter. And so using these two relationships that I received, or that I got, one from the Henderson-Hasselbalch equation, this ratio, okay, and so this equation I got from thinking about what we're doing. We're adding both of these solutions, or we're adding both of these substances to create a total volume of 1 liter. And so I'm going to go ahead and use both of these equations to help me cancel out one of the variables, or substitute one variable into another. And so this term right here, this volume of HAC, is found right here. And so according to the Henderson-Hasselbalch equation, 5.65 times the volume of acetate in liters is equal to the volume of acetic acid. And so I'm going to substitute this term for what this term equals to. So I'm going to take this whole term and I'm going to go ahead and plug it right in there. And so what I get is the volume of acetate in liters plus 5.65, which represent times this by the volume of acetate in, once again, liters. And that's going to give me a total volume of 1.00 liters. And so we're going to go ahead and treat volume of acetate in liters like X, right? We're treating this as a variable because we don't know what this is. And so we can treat volume of HAC as like Y, right? So this is Y, this is X. Okay. And so what I'm getting at is we can rewrite this whole expression to say, X plus 5.65 times X is equal to 1.00 liters. And that allows us to see that if I write my invisible 1 in front of that X, I can go ahead and add these two values. So that's going to give me 6.65 X is equal to 1.00 liter. And if I solve for X, that value that I get is simply going to be 0.1, let's see here, so this is 0.150 liters. And if I wanted to convert this into milliliters, I'm going to go ahead and move this decimal place 3 times to the right. And so it's going to be 150 milliliters. And so once again, X represents the volume of acetate. And so by substituting in these two key equations, one from the Henderson-Hasselbalch equation and the other just from thinking about the concept of the problem, I'm able to determine the total volume of acetate that I need to put in to my new beaker. Okay. And so if you guys recall, the total volume is 1,000 mils. And so if 150 mils is going to represent the acetate, then 1,000 mils minus 150 mils is going to represent the volume for acetic acid. And so if you subtract those two values, you guys get 850 mils of acetic acid. Okay, there we go. And so we've solved the problem. We were able to determine how many mils of acetate and acetic acid that's required to prepare this buffer if the concentration of our quote-unquote stock solution is 0.100 molar. And so we're going to add 850 mils for acetic acid, and we're going to add 150 mils of sodium acetate. And then we're going to go ahead and mix those two volumes together to create our 1,000 milliliter buffer. And so if the concentration and the volume is correct, I'll go ahead and do this in a different color. Let's do this in blue. Then the pH of that buffer should be 4. Now, if it's not 4, you can go ahead and add a little bit of acid or base, depending how far you guys are off from a pH of 4.